Ah, okay. Index storage. So this is a really boring graph, right? This is what you get on the Azure portal when you want to know about how much data is in your system. 2 blue lines. I don't know why they decided to put it as a line graph, but they did. So what's this telling us? It's telling us actually something really interesting that's not actually that clear to start off with. So I've got 65, 70 gigabytes of data stored, and I've got maybe 15 gigabytes of index there. This is a vanilla CosmosDB. It's just got some data thrown into it. Out of the box, CosmosDB is index everything by default, right? If you go to an RDMS system and you index everything in the table, what happens to the size of your data? It doubles. So you basically get all the data and you rewrite it all again in a different order, in a different pattern that satisfies your query. You just essentially double up your data. Did we double up our data when we had indexing all on CosmosDB? No, it's much smaller. And there's probably a few reasons for that. There's multiple reasons for that, but one of the critical reasons is the way that it stores index data. So what it's doing is, for each path in a document, it's going to store it as a data path. So imagine that document we saw before. I think there was an address in it. So you go, I'm going to make it easy. I'm going to switch out a couple in the same country. So in the document, I've got this path that says below the root there's a country, and below the country there's a value of this Germany. So that represents one attribute of value in one of those documents. So that is going to my index because it tells me about where my data is. And this is essentially going to have a reference to where the data is in the pages. So I get the whole document here. That's how indexes work, right? We have some information about one path in the data we're looking for, and then it tells us where all the data is. So if I was going to store all of that in my index structure, it'd be quite expensive. So what it does is it hashes each of these into like I think it's a 1 byte hash for this numeric part, which is the root node, and then a 2 byte hash for this piece, and another 2 byte for this piece, right? So I've got 5 bytes. If I store that string, how many bytes is that? It's going to be like a ton of bytes, right, compared to 5. Yeah? So that's what it's doing. It's condensing the data and putting it into hashes and putting it into a lookup table. The downside of that, the upside of that is you get really efficient storage on your indexes. Downside of that is you get hash collision. So it has to go in, so when it's looking for data to satisfy a query, it's actually getting an approximation of the data. Saying for this hashing algorithm, go and get me the documents that satisfy that, and it's actually going to get more than it satisfied the logical query, and then it has to filter them afterwards. But the brains in Microsoft Research have figured out that this is a far better way of doing it than trying to store the actual data in the index. That may change over time, but that's the way it is for now. Does that make sense? Yeah? Okay. And they skew some of these hashes. So when you have a path that's got an array in it, so we're going to expect like a number here. It could be 2, it could be 5, where it goes in the array. Most arrays in data systems are quite small. They're only between, like, say, 0 and 100 items in the array. So they skew the hash to make sure that there's more distinct values, hash values in the first portion of the integer set, less distinct hash values in the greater balance of the integer set.